is a bit kind enough, I can present only these two works of ours.
We have so many last time.
Okay, then, so this is the HFN2 monolayer, which shows the Rashba property, this valuetronic property, then this is the, uh, okay, and apart from our pursuit of our independent research in the field of computational nanosciences, we do collaborate with experimentalists and provide them with theoretical support. Alongside, we do this. So this is not a complete and an updated list, and I think that's it. In the interest of time, I skip this one as well, and thank you for your kind attention.
Thank you. Thank you.
And I'll be happy to take.
Yeah, I'm sorry, it's due to time limitation, and we have very kind of
schedule. It's understandable.
IT talks and oral presentations are also there. So yeah, it is not possible to cover all those things in such a short time.
Right.
So now just few quick questions. It's open for question. And let me ask one question.
Sure.
So if I just want to say it quantitatively for those piezoelectric 2D materials in comparison to like lead germinate with crystal, which is kind of very popular for. So can you please comment on that? How much picocoulomb per Newton or something like that?
Yeah. So for example, in barium titanate, you get something close to 100 picometer per volt. In MS2, it is 3 picometer per volt.
Okay.
But MS2 has its own place because in low power electronics, you need to generate a low power, low signal actually.
Okay.
You do not need to generate such a high voltage. But again, if you can by the use of the dielectric, it can be elevated to the level of higher voltage. That is also possible. But the purpose of this two-dimensional electronics or nanoscale electronics is low power electronics.
Low power. Then let me thank speaker again for such a wonderful talk. Now just as a talk
I would like to request our session chair to felicitate keynote speaker Professor Abir Sarkar with a memento.
Let's move to the next talk. Please check that pointer and other things is working well. Challenge by the time I read the introduction. The next talk is from Professor Abhishek Kumar Mishra on his metal oxides and 2D material for integrated carbon capture and conversion. So Dr. Mishra is currently working as professor at UPS Dehradun, and he's visiting scientist at University of Kassel, Germany. So he did his PhD from University of Lucknow in 2009, and then he worked as assistant professor at MIT University, Noida, and then moved to Texas A&M University for his first postdoc. He worked as EPSRC postdoc researcher at University College London from 2013 to 16. He also worked as DST fast track young scientist at JNCSR Bangalore and postdoc fellow at BHU Varanasi. Such a vast experience, and then he worked on this DFT-based calculation for gas sensing, catalysis, for CO2 conversion. He is recipient of various awards like DST Young Scientist Award from DST, New Delhi, and published over 80 research papers in various reputed journals. So now I welcome Dr. Abhishek Mishra. Please. For invited talk, 20 minutes and then 5 minutes for question.
Good morning, everyone. So I will be presenting carbon capture, utilization, and sequestration. So that's why the talk is like we are presenting CCUS at CCSU. I will be covering our work on transition metal oxides and new emerging 2D materials for CO2 capturing and conversion. So just a brief about why we are into this business. If you look at the data regarding the CO2, it's rising day by day, and hence we need to not only capture, we need to utilize that for some efficient fuels, and that's one of the strongest weapon in at the moment to fight the environmental challenges. There are various techniques. I'll not be going into details, but people initially were working on the capturing and storing, but that involves so much other complexity regarding the leakage and transportation, and then again converting it. So now people have shifted to CDU from past 10 years, and as I mentioned here, it involves a three-step. It's a three-step process where the this is a highly energy-extensive task where you need to have some good materials so that they can work on the lower temperature and other conditions. Because if you have to give the energy here, it means again you are putting some money into it, and our work is on the designing those catalytic materials which can work on the room temperatures. So we started working in this domain by we were fascinated by the copper because it can convert a large number of hydrocarbons. And even if you compare the oxidized copper with the copper, it's much more better in the form of hydrocarbon convergence. These were the initial motivations behind choosing the copper oxide-based materials. But when you try to model the oxides, especially transition metal oxides, you face a lot of complexity if we used to uh, work on DFT calculation because of the self interaction between the electrons. And then, of course, you have used the highly sophisticated techniques like hybrid functionals, but they have their own challenges in terms of being more compute extensive. So we use let's take the example of copper 2 oxide, which is a monoclinic crystal having some band gap and magnetic moment. But if you try to model it with the plain DFT, it of course fails. So these were the, like you can see, the finite states at the Fermi level. So, yeah, it also says that it's a non-magnetic material, which is wrong actually. So we used the Hubble parameter correction first to have a better model to capture both copper 1 and copper 2 oxides. And it's empirical type of fitting. You can see here that once you have a U is equal to 4, the band gap will start opening, and at equal to U equal to 7, you have in the range of the experimental. Then when you are modeling you are doing the calculation for stuff like a CO2 capture and conversion, you have a CO2, you have a water, you are not sure about the oxidation state of the copper oxide here. So it means our model should be strong enough to capture the both copper 1 and copper 2. So here again highlighting that the our U parameter corrections in this direction, and then these are the other technical details regarding how we calculated the surface energies. I will come to that point. Yeah, here, if you look at that, here we have the good range, but still, in the case of copper 1 oxide, the band gap is not matching well with the experiments. That's quite obvious because it has to be applied on the cases where you have the VBM and CBM, both bands are of the same localized orbitals. You cannot apply this to case of CU2, where you have states from the oxygen and the copper orbitals. And then once you have the correct picture of regarding the bulk material, the next task is to look at the surfaces. And before we move into the modeling of surfaces, you have to look into details of the polarity of the surface, because there are many researchers in which you will see that there is a type 1 kind of surfaces where you have a positive negative ions, but you have a perpendicular dipole moment in that. In that case, you have to reconstruct those surfaces so that you have a clear picture of your experimental surfaces that you can expect in your synthesis. So these are the these are well-known Tasker reconstruction regarding the same, and like type 3 surfaces where you have a positive, negative ions, but they do have some dipole moment perpendicular to the ions. So here what we have to do is to take some ions from the top and replace it at the bottom so that you can break the symmetry regarding the dipole moment here. So these are the Wolf morphology of CO2, and these are the facets plotted by calculating the surface energies. And you can see here the 111 plane is the most dominating plane in the CO2 morphology. And this is results regarding the copper 2 oxide, where we look at the different kind of magnetic content that you can have here. And then, of course, once we are done with the clear representation of our low index surfaces, then we calculated the binding energy of CO2 with the different these low index surfaces. As you can see here, this was the most stable surface in the case of CO2, and it shows the weak field reduction here, while the other surfaces which are chemically a bit unstable, which of course shows more activation for the CO2. So chemical reduction is being found here. And then we did further post-processing to confirm whether CO2 is being activated or not. So these are the beta charge analysis, which gives you the idea of how much CO2 is transferring charge as a result of the its interaction with the surfaces. And then these are the Phonon calculations to compare with the isolated gas molecule. And if you can have a look at these modes are changing their frequencies. So all these represents that CO2 is being activated on these kind of surfaces. And then we did the calculation regarding the conversion of CO2. As you can see here, the activation barrier calculated for the CO2 dissociation is quite high. Sorry. So this represents that okay, you cannot convert directly CO2 by dissociating it into carbon monoxide. So again, next task was to look at the conversion into methanol, ethanol, or methane, and for that you need to have a hydrogen source. So hydrogen can come from either from the water splitting or from the hydrogen gas molecule. So our results here are representing that it can come, I mean, this is very low barrier here, 0.1, 0.2 electron volt, and it is the same. So the results are saying that we can have the atomic hydrogen on these kind of surfaces readily, either from the water splitting or from the hydrogen gas molecule splitting into atomic hydrogens. And then we did detailed calculation regarding the format formation. So it can have two parts here, the carboxyl one, as you can see here, which involves a few intermediates as well. If you look at this part, this is the top of the this reaction characteristic diagram, you will see that it requires a very high barrier in case you are trying to form the carboxyl on this copper oxide 111 surface. This is the most stable one. But look at these only point 1 electron volt, 0.2 electron volt you really needs to have convert into the formate and then further formic acid. So our results here are denoting that these copper oxide based materials are well suited to form uh, to convert CO2 at the room temperature to the formic acid. To and formate and the formic acid, and it will not be forming any kind of carboxyl over. So, motivated by our simulations, our group there at the UK, they did perform some experimentation. This is a drift analysis for the copper oxide, and you will see here this is salmon pink representing the format actually. what they found, they started from the CO, and in the no time, they formed the CO2, and finally it was reduced into the copper with only one product. And you can see no methane or carbon monoxide. It was only formate for this. So they were puzzled by this and what's happening at the on these copper oxide materials. So we did simulations here. It was very simple to find out. We started with the pristine CO111 surface and placed hydrogen molecule there. And what we found that as soon as hydrogen comes here, hydrogen takes one oxygen out of the surface and forms water. So what's happening here? The CuO is getting reduced into Cu2O, and surface bound water molecule was getting formed. So what we can have here is when you have more and more hydrogen molecules over the CuO, as it was here, hydrogen gas was pumped in, then this CuO, copper 2 oxide, will change into Cu2. And once you have Cu2O, as we described in our earlier paper, here, then no time you will be having formic and formic acid formation on these plates. So that's what being experimentally found, and we explained it that how the surface is getting reduced to the copper oxidation state is changing as a result of water formation, and then once you have the this guy, you will be having only formate formation. So this was verified experimentally as well. And then similar calculation we did on the other copper oxide well, not to discuss these, but these are also very prominent results where we are getting the spontaneous formation of formate after the CO absorption. We are working on the defect formation and strain engineering on the 2D materials as well. And I mean, we started working on the copper oxide surfaces. We investigated the vacancies, and as it was expected that once you have the vacancies, you have electron trap sites. So we investigated oxygen. We were mainly interested in the oxygen vacancies here, and then you have more and more binding for these surfaces. So if you restore more and heavily activate, you can engine the defects here in terms of oxygen vacancies. So one of my student, Kamal, will be presenting this work where we worked on the side graphene materials, which are newly allotrope of carbon and being theoretically predicted. So what we applied the strain here, and as a result of this strain, you can induce the band gap here, and as well as the high CO2 activation on these side graphene materials, which are 5-7 rings here. I will not discuss more on this aspect. We are also working on the other materials like vaccines, and this stuff will be again presented by one of my student, Kamal. Uh, but what we are doing here, we are again engineering these materials for the efficient CO2 conversion. So I started this work on the MO2 TIC2 vaccines, where we engineered the defects and we plotted the electron localization function, as you can see here. And once you have this kind of data, you can accordingly investigate for catalytic applications specifically. So as you can see here, these are the electron trap sites, and then we got high CO2 activation on these materials that we published in Journal of Material Chemistry a few years back. We have been working on the other two materials as well. Like recently, goldene is being synthesized, and first it was computationally investigated few years back, and we investigated these materials for CO2 capture and conversion, and this was recently published in BCCT, where we have found that if we have the time vacancy defects here and boron dope structure specifically shown very high boron and nitrogen dope structure shows very strong CO2 activation of these surfaces as a result of charge transfer to the golden seed. So these are the work Kamal is working on the 2D materials on the CO2 capture and conversion. Anjali will be presenting a talk on machine learning based simulations for the band gap prediction of 2D materials. And then Abhishek is also present here. He will be presenting the iron oxide 2D materials on which we have a certain project where we are working on the two-dimensional transition metal oxide, which has been recently people have been able to synthesize. And so we are working on the experimental aspect as well and computational aspect as well. Anu will be presenting work on vaccines as well. And Deepa is not here, but she is working on the metal clusters based super interaction. And Nitin in my group, just to mention, we are working on the molecular dynamic simulations on the better alloy materials for the aerospace applications, where we are working on the grain boundary mitigation and looking at the stability of those nickel copper alloys at high temperature. That's it. I would like to thank the SURF DST for funding and my collaborators at the University of Leeds, University of Kassel, University of Southern University of Denmark, and computational facility at the UK. Thank you.
Thank you.
And now, if you have any questions, please.
Yes. Now floor is open for questions.
A very basic question. So in very simple terminology, we took carbon oxide from environment. And what we did, CO2 we took. And what we would like to do, we do H2O, then we will convert into water, we separate. What actually we are trying to do with all the research?
So
We are extracting carbon dioxide from the environment. Then after that, what we are trying to do?
There are a lot of research in various domains.
Okay, correct.
There is one thing that you're only working on the capturing and storage and then converting it. But there are, new working direction are to work on the dual functional materials, where you eliminate the use of, extraction of CO2, which requires a high amount of, again, energy. So, the main research was focused on the catalytic materials, which can work on the normal conditions. Without giving the high energy in the conversion, uh, we are working on dual functional materials where the materials can not only capture but can convert as well. So there are other methods people do use, like transportation. Once you have captured, you can store it.
Prototype or some applications has
Yes,
been used in
yes,
industry
yes, yes.
so that we can extract from industry point of view of
Yes,
the application point of view,
already
from
being-
traffic point of view.
Yes, there are already people who are working on it.
Actually, still it is not in market right now.
I mean,
As on date.
it's available. Even still, people they are working on this regarding. But again, the challenge is to minimize the cost. Actually, minimizing the cost in terms of new catalyst development, or the challenges are there in terms of leakage of CO2 when you store it.
Cost when we are talking about cost related to your production or when it is being for sales and service means when it is in the
Well,
open market.
I am mainly concerned regarding
Your cost.
the conversion.
Your cost. Your,
Yeah, yeah.
your
But there is, of course, the cost factor is, of course, everywhere.
What about long time back we hear that they put water in a glass of copper. So पुराने जमाने में कहते थे ना कि कॉपर के ग्लास से पानी पीने से तो कॉपर अंदर जाता है ऐसा है नहीं है when we are talking you are research scholar I am not a research scholar.
Well, Utna, I think that's a very small amount of things you are discussing. We are not looking at that aspect at the moment.
You
Yeah.
talk about copper and then water like this, so I
Yeah.
thought it is some related or not. It is not related. Your research is not.
Yeah, we are not in that particular aspect. But yes, there may be some minerals which are useful for our health. but I think that's a very small amount of copper.
Copper comes out or not? No, because in Ministry of Health, अच्छा, अच्छा, because अच्छा, अच्छा, when we went in trade fair, Bharat Mandapam, November, December 2024. So under the head of Ministry of Health and Family Welfare, they said it is a myth actually. They have posted out in the Ministry of Health, there was one stall. The copper cannot go inside the body even if you put you got my point what I meant to say. Yes. Thank you, sir.
Thanks. Thank you. Yeah, it's a bit beyond the scope of this, but I wish that your student may soon start up or something for this. So thank you. Let's thank Professor Misra for such wonderful talk.
Thank you, sir. Now, I kindly request session chair to felicitate our invited speaker, Professor Abhishek Kumar Mishra, with a memento.
We move to the next talk from Dr. Pradeep Kumar from CSIR M3 Bhopal on 2D graphene and vaccine. So Dr. Pradeep Kumar is currently working as principal scientist at CSIR Advanced Material and Process Research Institute M3 Bhopal and associate professor at ACSIR. So he received his PhD degree in physics from School of Physical Science, JNU, New Delhi, postdoc at KAST and KIST, South Korea, and then he was PhD Inspire faculty at VRC Mumbai, Central University of Rajasthan from 2016 to 19. He joined this current institute, CSIRM3, in 2019. So his current research is interested on 2D materials, and now you'll talk about this. He has several book chapters, 2 patents, and currently working on 5 projects funded by different agencies, funding agencies. So floor is yours, Dr. Pradeep.
Very good morning to all of you. First of all, I would like to thank organizing committee, mainly Dr. Dheeraj Pawar and Dr. Malik for inviting me and giving me a chance to present some of my research. I'm working mainly on the 2D graphene and MAC, mostly experimental work and some application as well as some fundamental work. I'm mainly working on the experimental work. So my research actually at CSR M3, mainly I am synthesizing graphene, mainly graphene oxide and CVD graphene as well, and other 2D materials like Maxine, MOS2 also, and their polymer composites for variety of applications. And 2D material based thin films, foam, aerogel, and composites for thermal management application, EMI shielding, hydrogen storage, and electrocatalytic applications. So particularly, I'm engaged with different projects funded from the DST, SERB, CRG, CSIR, DBT, and ICMR. And these are the PhD students working on the hydrogen storage, EMI shielding, electrocatalyst, and thermal management, and hydrogen storage. One SERB GARP student. So, 2D materials, a lot of discussion on different kind of applications. Today, I will focus only on the hydrogen storage and electromagnetic interference shielding application of graphene and maxim-based materials. So, plan of my talk. First, actually, we need to understand why hydrogen storage is important. Generation also important as well. Transportation also important. Utilization and storage actually also one of the major challenge in hydrogen energy. So, and then graphene and maxim-based materials for the hydrogen storage. And then in last part, actually, I will discuss some of research graphene-based materials for EMI shielding applications. So, why we need hydrogen? Actually, as we know, hydrogen is available in nature, not in like free form, but in in H2O and some biogas, biomass. So, like there is lot of possibility of hydrogen, and so it can be like an alternate material to the carbon-based fuel, like petrol and diesel, and it can be also produced from the variety of sources like water splitting, coal gasification. Like it is not other renewable energy like wind or solar. You have dependency and limitations. But in hydrogen, actually, we can use different kind of like source to generate the hydrogen. And when you couple the hydrogen with fuel cell, it will produce only the water, no pollutant. So hydrogen is like considered as a green energy. And the main important thing about the hydrogen, actually, it's a high energy density, 120 megajoule per kg. So it is almost 3 times of the petrol or diesel. So this is a major factor to use the hydrogen as a fuel cell device. So developing hydrogen as a major energy carrier, it can solve many future challenges. These are some physical properties of hydrogen, like density. The main actually problem with storage of hydrogen is density. Density is 0.089 kg per meter cube. It is 1/10 of the natural gas. And the density in liquid form we can achieve up to around 70 kg per meter cube, which is still 1/6 of the natural gas. And the main important thing, as I mentioned, energy per unit mass, 120 megajoule per kg, which is almost 3 times of the gasoline. So this is the main driving force for the hydrogen to use for as a future renewable energy. And this graph is showing actually this comparison between the volumetric and gravimetric density of different fuels. We can see in hydrogen, either in liquid or compressed form, we can achieve the gravimetric energy density is the highest, but actually the volumetric density is very low. So we need to, like for the practical applications, we need to compete with the existing this carbon-based fuels. We need to increase the volumetric density. So hydrogen energy actually basically divided in 4 parts: hydrogen production, hydrogen storage, hydrogen transportation, and hydrogen application. I will focus mainly on the hydrogen storage part. So, in continuation, hydrogen energy, as we know worldwide, actually now focusing. So, in 2023, in January, Government of India Union Cabinet also announced a national green hydrogen mission. The mission aims to make India a global hub of green hydrogen production, utilization, and export. And the key component of this mission is to establish a conducive research and innovative ecosystem for green hydrogen in the country. So, the Green Hydrogen Mission, Ministry of New and Renewable Energy prepared a draft for this R&D of green hydrogen ecosystem in India. And the key objectives, actually, this draft, actually, they have covered all the component of production, storage, transportation, and application part. So, mainly I am focusing on the hydrogen storage component of this draft. So in this draft, actually they mentioned the key component of hydrogen storage in India actually to develop efficient, safe, and cost-effective hydrogen storage methods for high-density storage, reduce leakage like in cylinders, and allow for easy and quick refilling, and to develop the materials for high gravimetric capacity with fast kinetics and high cycle life at operating conditions. And indigenous development of type 3, type 4 compressed hydrogen tanks. Actually, in India, still we don't have the facility to test this type 3, type 4 cylinders infrastructure. And the synthesis of allow and other materials used for the solid state hydrogen storage. And to develop indigenous solid state material based hydrogen state canisters and tanks. So hydrogen, coming to how we can store the hydrogen, either you can in material form or in physical storage. So physical storage we can use in compressed form, as we all know, and liquefied form. This actually liquefied hydrogen already used for the this NASA and other that kind of application, space application. So if we store the hydrogen at 350 bar, we can achieve 23 kg per meter cube density. And if we store the hydrogen at 700 bar, we can achieve maximum 38 kg per meter cube density. This density is still very low compared to the petrol and diesel. So, and this also compressed form also have some issue of like container rupture or leakage issue, because we are storing hydrogen at very high pressure. So we need to design the cylinders like type 3, type 4, and type 5 also very carefully, and the valve also need to be very carefully we need to design. And in cryogenic form, actually, we can store hydrogen and we can achieve the density 70 kg per meter cube, but actually it needs to external energy input, because you need to liquefy the hydrogen and then store it. Still, the density is very low, and also boil up issue also. And the other part actually material storage. In chemical storage, you can like two way. Either hydrogen will make the covalent bond, or it will be like attached with the material and physically. So we call it Actually, either this adjunctive, I mean this typically adjunctive. I mean this typically adjunctive one material. Uh, explored and also explored this decades. In adaptive, actually, the hydrogen will store in so carbon-based materials, MOF, COF, and graphene and CNT, and now Maxine also explore. And this table actually shows the comparison of different hydrogen storage in the we can get very low. We can achieve with uh, 425. Liquid organic hydrogen. We achieve the storage capacity what is recommended by the DOE US. But actually, either they have the temperature issue, operational temperature issue, or the pressure regulated capacity. So the solid state materials is still not optimized. Either actually have very slow parameters. So materials still need to optimize. Now, just want to give an example. Suppose you want to use some device. If you drive the car around 400 kilometers, hydrogen. If you use this like compressed bar and 200 bar, still you need 110 liter container to fit your car. And if you use the liquefy hydrogen for that process, you need the 57 kg container liquid hydrogen. What is this? In land, but actually we can reduce the materials development, we still can reduce it. So I will solid materials for kind of so there are like they have some advantage like we can store hydrogen in solid materials more completely cheaper. This could be hydrogen like in case of directly we can store the hydrogen in optimum temperature and pressure, and we don't require some challenges also. Solid materials. Challenge. Cyclic stability. Like materials should not just one cycle you fill the hydrogen and also material should be reverse with. Once the material should have like again the hydrogen. So reverse with also. So vaccine. These are the some parameters set by the Department of Energy USA like gravity ultimately 6.5 like durability or operability and operational cycle stability should be 1500 and minimum system fill time should be like some from the Department of Energy USA. So and coming to the like graphene and vaccine, why they are important? Actually, first they will be very lightweight. They have high surface area like graphene, 600 meters per gram. Lightweight should be vaccine also reported 93 lightweight, and we can tune the property by the utilization and doping. We can tune the earlier the some surface and storage. Dynamic also is stable up to 800 and we can achieve the moderate absorption energy. We have shown the reversibility and good cyclic stability. So these are the lines graph, bar diagram. And for a research article published between 2000 to 2023, like in graphene and heteroatom of graphene. Heteroatom basically to increase the binding energy of the hydrogen as well as the hydrogen. Uh, Uh, I started synthesis single graphene oxide. We have modified the method, and this around if we graphite flake, 95% of graphite flake can be converted into the single layer graphene oxide. And this graphene oxide we characterize using the FESCL and XRD characterization. And, see this multiple kind of forming the liquid kind of behavior, which is almost this graphene oxide actually we use lithium evaporated with dioxide in the graphite we converted into graphene. So, two oxide. That again, when person has resistance capacity. So, this daily junction. So if the different side level property, like magnetic property, we increase the, I mean, the large size showing the more capacity. The binding energy around 20 kilo. So this is like efficient binding energy. And next part, actually, I will quickly move. Recently, we developed reduced GO and PVDF composite central for the EMI series. 70 by see the graphic line, and we can this fraction of 6.75%. And recently, we have also developed the reduced polymer sponge for the EMI shielding and water oil separation application. And this sponge actually almost like recover once you press 95% it's recover. And we can use EMI shielding as well as for the water oil uh, within a like flexible like all the oil. This material. And we have tested for more than 10 actually like petrol, diesel, kerosene, different kind of solvent, organic solvent as well as oil. You see, there is no like petrol, only water left, and immediately like you can get the petrol here. And not only graphene mixing, we also explored like some aluminum foam for the image applications, very light. And recently, the diesel suit for the were showing very good performance for the lead detection. Nanofiber based pesticides. So, thank you very much for your time.
Thank you, Dr. Pradeep Kumar, for finishing the talk. One more questions.
Storage, when we are talking about the storage,
Yeah, actually, there are three options to storage. Either you compress form or in liquid form or in solid materials. So solid materials actually, yes, ultimately up to will come up to fuel cell.
how much I just suppose I have a car.
Hmm.
Basic, we are practical. I'm talking about design. It should be. So it is still it is in process.
Yeah, actually, it's like compressed by even you maybe know and NCL, Pune, and KPIT. They have launched a bus, but they the bus is depend on fuel timing based on the fuel cell, but they use the compressed form. So compressed form actually hydrogen. So you use very large scale of compressed. So ultimately, size of drag it. The hydrogen in molecular form or in atomic form or in between solid materials, and then you using the you can extract the hydrogen, with dehydrogenation, and you can use it the transport. I mean, car or bike. Yes.
When you were giving the sport, are there any cases since you are in this field, because
Thank you. Yes, sir. Sir, next one.
So that 173 Kelvin, the hydrogen is, the
One-
absorption is quite high.
173 actually we can I think in for practical application minus 50 to 50 or 60. So for actually we actually our target to at ambient conditions I mean minus 50 to 50 or 60. Once the prototype and then
Also down
no here yeah actually the cryogening in it actually you may know.
Yes.
Yeah, the system actually there is option you can use up to 77 Kelvin. Yeah.
Yeah, my colleague also work on this. He uses this Krishna analog. Also, he showed around 4%.
Yes,
hydrogen,
yes, yes.
but at low temperature.
Yeah, low temperature. I mean, basically from the body temperature of the difficult. So now let's no methanol, ethanol. Again, you like methane reforming. I mean, the you will CH4. You need to break it first. Actually, then you will have to come the production part because first you need to production of the CH4, and then you will break into hydrogen. No, mainly focus on the green hydrogen production. If water is collected, you need to prepare good opportunities, good like PEC membrane and this all. So focus on the green hydrogen. For India, I think coal gasification and methane reforming, they already producing around 6 million metric ton hydrogen in India, but this is the target.
So let's well, I think thank you for such a nice talk.
Now I would like to request Kumar presenting in a moment.
By Dr. S. Rajgopal Reddy. So Dr. Reddy is he obtained his PhD in theoretical chemistry at University of Hyderabad and then worked as postdoc fellow University of Wellington, Nuremberg, and then University of Freiburg. Since 2020, he is working as assistant professor in Rajasthan. So he will talk about this triplet state generation in timers.
Okay, I thank the organizers of OMC opportunity. Today I'll be talking. So today I'll be talking about the triple state generation in the body fluid and other body fluid. So triple state generation or access to the triple states is of a very problem. Um, so the material shown here, the body fluid, other body fluid, high living, for example. And each generated from the body fluid and the body device, they have found the application. Um, I have I have given you the number of publications across the year, and these are all working from the uh, uh, okay. Applications which are I'm talking about is the photodynamic therapy and the photothermal. So where you have a chromophore, then you have when you apply the chromophore, you have to go to a triplet state, and the triplet state will involve oxygen into a red oxygen, which is a negative oxygen. By the or form the chromophore can principle convert into the triplet state. In this triplet state, it will come back to the ground state, non-reactant process, in which it will generate heat. Right? So that will be called as the P thermal. The possibility is that, for example, you have the chromophore. The chromophore can interact with the next system can energy able to harvest for electrons. So I'll be talking about the image quantum device. There are two mechanisms. I this is the Jablonski diagram. Have the response state, and from the triplet state, you have to connect the RGISC. Share, and then the associated ISC. So in here, you have the protein chromophores. Chromophores are in the autonomic orientation. Then associations have the here is a link. ISC, right? Um, and the other possibility is the segregation, as I have already told you. So where you have one monomer, molecule both are ground state, the initial separation goes to one, and then there's one zero of the and to where you have sufficient the surface squeezer effect. And beyond, if you want to get, then you have to use the multiple expression where here you can see that the efficiency goes to 45%. So maybe a few important points. For example, here we see that the important is the duty state. So few important parameters. For example, if you want to have the setup, the energy of the T1 and the T2 should T1 and T2 should be also connected to suppress the energy. This is a mechanism of the synchronization where you can go from the chromophore 1, the S1 to the DT. So essentially, in the ISF and the associated following to the CT stage, you can in principle access through ISF or the body to is characterized by with the fundamental first the S1 energy and the T1 energy and the person's later because we have to transients that technique is the piccosecond or the nanosecond. For example, you will see the over here, and this is the color is the delta volt. So to the you can calculate in principle of being depleted, and not much information about the formation of the crystal state because you may have some sort of understanding of of the T1 to T2, you may find it, but it's difficult for us to understand the how this zero. For that, you have below this is sorry. The pattern of the principal temperature to test. So here I have shown you the modified diamond and the two numbers kept in the orthogonal position to have the dimer the in the non-polar solution. Here I the main is would be around the positive or the transient forming around the 400 nanometer, and this is the triple stage. And also they have calculated the case. So, but then this hypothesis or the interpretation in the atomic body dismissed to the EPR spectroscopy and also high level differential calibrations. Because the body PYs are very highly correlated molecules. So you have the principle not the multi the condition. So now the question is whether you have the ISF or the segmentation or the associated ISP, the modified demos. And here I have another experimental calculation where the authors modified demos here is not accepted. Uh, so you have actual diamond here. And importantly, I want to show you that this is the delta OD. And I want you to show that big region over here. Region is immediately having the delta OD positive. That means it's a new coming up. And this transient is the also they have calculated the delta L, that is the versus G, and we have the delta. The delta is the inversion of the of is the step one. The G that you have non-native channels are existing between these two. So what of the effect states in the body fluid dynamos through and to calculate the diabetic state and to understand how fast the from how much the transient can transform into other states. So to understand the traditional conversion mechanism, whether it's the CCSC, also we like to see the structural effects on the we want to calculate the effects of these. This is the chemical methodology where we calculate the potential, and when we calculate the potential surface, there will be exception between not in principle use one single PES. You have to use the both of the PES. Uh, so for this, we go beyond the diabetic representation. We have to go for the diabetic representation between these surfaces. This in terms of the and the potential energy expanded in terms of the places and we in between, and then we have performed the quantum nuclear dynamics. So the optimization is done at the BCM level theory, but the level of theory and the eccentric level of theory to include the and we have looked into different active spaces. So the importantly the active space is the body PY, and we have the diabetic couplings between so I'll briefly give you two important results. For example, I have shown you the energies for movement. I want you to pay attention to the strong dipole moments for the electronic states. These dipole moments can change the dynamics when you have and also I want you to pay attention to the F1 is mostly local state two, and the remaining are the WFMs be included in the TDDFT level here. And this is the Japanese example. These are the local active state, local orbitals. For example, you have one monomer here and one monomer, and the HOMO is localized on one monomer, and the other HOMO is localized on another monomer. Is the LUMO and is the LUMO. I have calculated Means that from one state to other state is for example, you see that VDP S1 S0, this is the direct coupling. Only we have 52 milliamp volt, and for the V28, it is quite stronger. Then PP between A. This is we are talking about the charge transfer period mechanism. So the couplings are quite strong. When you compare with their fantasy, the couplings are stronger than the fantasy. And we have calculated the effective coupling between the species. For example, the direct coupling here is 52 milliamp volt, then the species 16 because of the even though you have strong coupling between them because of the symmetry. The so I wanted to place 8.62 is negligible in this particular diagram. Then we have calculated the little surfaces by optimizing geometry. So we start from the zero and then we make it uh, 5. Right. So I want to see the surfaces. These two are the uh, at the 90 degrees was the orthogonal geometry. And you slowly started going away from the 90 degrees. And you see going up around 3.0 at the 90 degrees, but then in reality, on to the volt is very high. So here I have shown you the mixing of the states. For example, the blue and the green are the so for the S1 state, which is completely coupled with the other several states, so you see that the character is almost fixed. So it's not good. However, you have uh, the S2 state. S2 state is the over here. The S2 state is to one lead to composition. The generation around and then we have looked into the surface of the 2 8 where we have and because of the the diverse you have so in the diverse yeah so the diverse you have the metal group of here so the not investigate the around the top of here consider only the surface is to the 100 degrees and you see that the surfaces are completely in a mixing together. That means that the so the hypothesis is that the dimers when you are in the orthogonal position, then there is no light, so emission is not generated. However, you allow the molecule to rotate along the horizontal angle, then molecule state is on the you cannot use the GN. You ignore the so finally, I'd like to show you the lifetime. Here I have one particular timer, one particular timer, and from the surfaces you can get the coupling parameters, and by using coupling parameters, you can simulate the absorption spectrum. And yes, and we have simulated the dynamics. So here our interest is to show the lifetime You have the ground state, 88%, and you have, the CT and the MEH are there. As the laser field is down, and the width of the laser pulse is 250 seconds. When you check the laser, slowly the state is slowly start acting out, and also you have the so that we initially hypothesized you have both the ME so participating in that. So and you have two times the 20% over here, and the CT state is around 20%. When you energy of 1.3 electron volt per fourth state, more amount, you see that there is transfer. Right? So the ground state is around the same. So into population elite state, and also the so our hypothesis is that the CD states are so the CD states form play an important role in the dynamics, and we show this here. And this is the work my people, and I thank the organizers for the opportunity and CRB and the UC Startup Grant for the funding, and thank you to Rajasthan for the
Thank you, Dr. Reddy. Open time.
You will respect your hard work. Only one question is start of the conference you were talking about related to cancer cells.
yes.
Can you please, when you guys, can you please explain me how you are killing the cancer cells? Means what is the basic concept behind it?
All right. Yeah.
We are not discussing
Yeah.
what is how you will or how we treat cancer cells. Head cancer cells are in which organ of the body? Just like the prostate, maybe there's what
No,
specific
I
organ you are
can't
talking
answer
about?
that question because I'm a theoretical chemist. But I can tell you the mechanism how it works. So here, for example, the idea is to generate the difference. So now we have this chromophore. So what the chromophore is done, we need the so wherever the cancer is there, chromophore, usually because the light should not uh, chromophore goes to the and this different state is pathway. For example, the spinal coupling chromophores is very that means that it has to spend a lot of time in the different state and it has to come back to the be done through unmediated process. It has to vegetate and then it will go as a different. So because of that, tumor cell is similar. So humanly, they have found that they have injected the chromophore to the rat, and then they have central light, and then they have saw that the temperature is to so that temperature is enough to kill the cancer. Or that other possibility is in the prototype, sorry, the singlet the chromophore and with the oxygen. We found this is called as seduction.
any practical machine?
No, no, they have yes. In So I can give you the paper. You can find it.
Thank you. Let's thank the speaker. Wonderful computational work.
Thank you, sir. Now I kindly request session chair to felicitate and invited speaker, Dr. S. Rajgopala Reddy, by presenting him memento as a token of appreciation.
As we are running with behind the schedule, so now we will start the oral presentations. So I think tea may be there if somebody want to go and grab some tea, but we will continue the oral presentation here. Okay, so we will continue. The first oral presentation. So all the oral presentations, because now we have to select one best oral presentation also. You have to be very careful for within the time criteria to judge for the best oral presentation. So first is Mr. Kamal Kumar from UPS. So 10 minutes are allotted to all oral presentation for speaking. Just few quick questions. Okay, so Kamal, 10 minutes.
Hello. Good afternoon, everyone. I'm Kamal Kumar. I'm pursuing my PhD from UPS Dehradun, and I completed my master's from Department of Physics. And right now, I'm working on carbon capture and conversion techniques under the supervision of Professor Abhishek Kumar Mishra and Professor Joe Steller. So, coming to the point. So let me give you a quick introduction of my work. Actually, right now we are facing two major challenges. First one is the need of CO2 capture. As we know that the regularly increasing temperature and global warming is harming our environment due to the excessive emission of carbon dioxide. And second one is lack of fossil fuels. We have very limited resources. So for capturing part, we need adsorbent materials. For reduction, we need catalyst. So what are tasks? What we are planning? We are trying to design a single material, which is called dual function material, that can capture as well as convert the capture into another fuel. That means it can work as a adsorbent as well as a catalyst. So this technology is called in carbon capture and utilization. Use the most of the Now, the main challenge in CO2 activation, or I can say when we will say that this material is going for CO2 capture or not, is that low absorption energy. The traditional materials that have very low absorption energy, which is the widely most graphene is most widely used material for the absorption energy of CO2 around only 12 So the criteria for an absorption material is 35 to 48. The second challenge is bending of CO2 molecule. The CO2 is a linear molecule, so material is CO2 when it adsorbs from the surface. And the third one is when CO2 adsorbs in the material, reduction of CO2 starts recently. A vaccine is experimentally synthesized, which is TIVC, titanium vanadium carbide, and it has two types of signature. This one is this coherent TIVC, and second one is solid solution TIVC. In coherent TIVC, there are vanadium atoms on one surface or one layer and titanium on other. While in solid solution, the atoms are more arranged in any surface. So we targeted material using capture and conversion plant using DFT because it is a powerful tool. It provides. Now we started our study absorption on OTIDC as well as STIDC. For OTIDC, found right the origin of applications and found that the absorption energy and earlier shown around 35 48 kilojoules per there, but second criteria was that the bending of the CO2 must be there. And we can see here that the linear CO2 molecule is bended with a bond angle of 1.5. So this was the second challenge. One was the there should be a negative charge transfer on CO2. And by better charge calculations, we have charge transfer also. The charge transfer on CO2 is found minus has been activated and this is a suitable material for CO2 conversion. Now, what about solid solution? Where the atoms are distributed both surfaces. Similar kind of result we have found that the energy is around 26 kilojoules and the bending of CO2 is also observed. PIDC in pristine form in both water as well as solid solution are found. Very synthesized. This is completely theoretical model that we have monomer material. And vaccines are there are various functional groups present attached to the surface of the medicine, like the oxygen functional group, chlorine, OH functional group, sulfur functional group, etc. So, for more realistic model of our vaccine, we have studied CO2 activation on disease. So, like this with oxygen atom, these are red atom are the oxygen atom, uh, chlorine atom, and its sulfur atoms. And we found that CO2 is very, very weak like PIVC mixing. That means oxygen, chlorine, sulfur mixing, or PIVC, these are not suitable. Similarly, we have done for solid solution also. Oxygen, chlorine, and sulfur. Option no penalty of it is due to steric indifference. Generally, found that when atoms on the surface are right, like of material. This phenomenon is so slice part for DIBC both ordered and solid solution is not suitable for you. But when this material was experimentally synthesized by HPS and other experimental studies, it is not that also present there. And that is actually for CO2 conversion when we try to convert so or another like momentum or maybe any kind of species motivated by this outcome, this experimental outcome, that there is a presence of one function group studied CO2 activation on slight PIPC as well. And OH functionalized PIPC, here are the OH. Here it is STIVC also. Complex molecules spontaneously information of hormone formation arises from the structural parameters. We have compared the bone length and bone format iron with already available experimental values in literature and they very strong and very agreement. Another one is that formate iron has negative charge So by metal charge transfer, from that means DIVC magazine can spontaneously convert the captured CO2 to format. Which is actually what we are so here is the resultant waste to ODIVC it also converts the CO2 that is spontaneously into format. So DIVC magazine with oxygen functionalization in both configurations, ordered as well as solid solution, is capable of converting CO2 spontaneously into format. And these are the conclusions from the pristine as well as post IBCR for reason. Apart from this IBC, we are beauty materials like gold, doping and for CO2 conversion. Chemistry. Other beauty materials like graphene. So I will last I want to acknowledge my supervisor, guidance and my supervisor, Joseph Adam, and so from my side. Sir, actually, it is not for storage, it is for conversion. CO2 directly comes in the contact of the IVC and is spontaneously converted into format. No need of storage is there, no need of extraction is there.
But in conversion into
Format ion. And it is format is a reaction intermediate. It can be further converted into ethanol, methanol, and included ethanol.
Okay, so if there is no other question, so there is some change in the program, and first we will felicitate the session chair. Okay. So, Mohit,
Good afternoon to one and all present here. My name is Anjali. I am working under the supervision of Professor Abhishek Kumar Mishra. And today I am here in front of you all to give a oral presentation on the topic precise prediction of stability and band gap for 2D material using machine learning. So this is the outline of my talk. We first will use why we are doing this work and why we only gap and stability, why we are choosing machine learning. I listen. Sure. So we all know with the advent of graphene, the domain of the 2D material has seen a very major evolution. As we go from the bulk to the 2D, properties of the material changes drastically. For example, graphene is a bandless material, but the mobilinium disulfide, that is MOS2, it shows a direct band gap of 1.8 electron volt. And as we changes from the bulk to 2D, and the electrical so on these changes drastically. We have chosen band gap. Band gap of a material is whether a particular material is a metal, semiconductor, or an insulator. and then we application. Properties that we have chosen is stability because for sure the material has to be stable and then only initially there were traditional methods like experimental approach. Then people came and right now the approach that is we are using ML to make our life more easier. So I'll just give a very basic brief about how ML is implemented. First thing to perform ML, we need a lot of data. For data, we have databases like C2DB, that is Computational Turing Material Database. Then we have Multi-Test Project, and we have Cambridge Structured Database. Apart from these, for various applications, we have different databases. We have the data model. The model we also have the data. And after that, we are training the model. And last, we do the prediction. And these prediction depends on what applications. For example, if we do it for the battery related applications, we target the electrode materials. We are using it for the polymers, high glass transition temperature. If we are using it for the process, we target the activation energy. And in glass, we have the solar cell, if we can target the band gap absorption coefficient, etc. It depends from application to application what property we are trying to. Based on that, we can do the prediction. For example, these are two examples. In the first example, the author or the researcher they have activation energy for 788 catalytic reactions. And not only this, but once we are done with the reaction or the prediction, we make the work easier for the future. Because once we have predicted, now given new compound, so this was the previous work done in which they have predicted the band gap of 2D material using four algorithms. This what they have played around with the feature selection with the descriptor that we say. These are the descriptor which they have used. So in the last we can see gap NOC, that is gap without spin orbit coupling. So when they have not used it, they have used the benefit that you see. This in their model occupied of accuracy of 44%. So what we have done, we have instead of directly predicting the band gap, we have first chosen the stability criteria. First we choose, okay, these are the material which is stable. And for that we use a eval. That is also a feature that we got from material data. After we got, okay, these are the stable material, then we predicted the band gap of those materials. But also we have to do the sharp analysis and inside the machine learning model. So these are the results. We have random forest, XGBoost, and CAT. These are the highest accuracy that we have got from these three models. And these are the plots. These are the three models that have shown the highest or the very excellent fit for these gaps. At last, we had shown, okay, these are the shape analysis, but we have the prediction about which features has shown the which features is responsible for the better predictions. So for that, we have used the shape analysis. Yeah, that's it. So I'd like to acknowledge my supervisor, Professor Abhishek Kumar Mishra, my teammates, and UPS for this.
Yeah. Thanks, Anjali. Now, session is open for question. Any?
Where
Yeah.
you will use machine language, where you will
Machine
use
learning.
where
Machine
you will use
learning.
binary digits, है ना? Where you will use that.
So it depends on that's what I said that it depends on the application. For example, if I'm working on solar cell, it is there. If you're working on catalysis, it is there.
So machine learning will be used everywhere. It's not only for this. It's a kind of new, like na AI to recognize. So the model is there, database is there. They will extract a database. Based on that extract data, they will predict a model. Okay, model of theory, model of experimental results, anything. And then hypothesis analysis. So machine learning is similar like AI. How machine or your equipment is well. Okay. So next talk is by Praveen Kumar, SSV Hapur. So next one, Sukmani. CCSU Meerut. Okay. Yeah. इसका है ना पीपीटी हाँ करो स्टार्ट करो वृत्तिका वेर इज वृत्तिका
Good afternoon, everyone. I am Sukmadi Astogi. I am research scholar under the supervision of Professor Anup Kumar sir in CCS University, Meerut. I would like to thank the Department of Physics to organize this conference in International Conference on Frontier Materials. Now, I am presenting my work computational systems and non-linear properties of phenyl benzamide. These are outlines of my work. Firstly, I will discuss here the function theory. It's working. After that, nonlinear optical phenomena, nonlinear materials, molecule themes of phenyl benzamide, objective of my work, computer here, optimization, analysis, orbital analysis, non-covalent interaction analysis, nonlinear optical parameters.
you have 10 minutes only
First, we have discussed density function theory. Density function calculation can critically analyze nonlinear optical molecules is most popular and versatile method for determining various properties of molecules. DFT based on Hornberg and Johansen theorem to treat many electron system and approximation values. Mathematician and physicist on determines all the ground-state properties of the for many electron systems. Density function theory is define the property of many electron system by using functional function is another function. Many body quantum mechanics in terms of electron density. For other like Avicii and semi-empirical method, if we have many body problem like then one electron in a calculate sorry wave each and every electron density function sorry wave function working of DF. Only to one electron problem we can solve Schrodinger equation exactly. We have to solve involve property. The Nobel Prize in Chemistry in 1998 was divided equally between Walter and John F. Wheeler method. Non-linear optical phenomena of the invention of light to a material. It is basic diagram goes to second harmonic generation process. Now, intense electron can ways as molecular microscopy. Molecular polarization can be described by field-dependent molecular dipole. Mu out or beta dot gamma dot and usually intrinsic moment of molecules alpha beta polarization per unit also called P over of naught E dot phi respectively for second order susceptibility of material. Nonlinear case number specify four criteria. Bright resistance, resistance to optical damage, nonlinearity, optical transparency, application of nonlinear materials, data storage, optical computing, laser display, telecommunication, optical bond length, bond angle, and torsion. Micro molecules, nonlinear behavior, analysis, for can be an non-covalent interaction for nonlinear optical dipole moment, polarizability, and hyperpolarization. We using in my study Avogadro Gaussian. This is my molecule I studied. Chemical organic optical molecule orthorhombic system with space group is molecule experimental studied at all. These are latest parameters. This is result discussion is result generative optimization. This is a figure. CMLDB molecule have been calculated by DFT. This is version 09W package and obtain geometry. Benzene is substitute and a carbonyl group. This carbonyl is part of benzamide where the nitrogen atom is bonded to phenylene or these are optical. Angular and torsus angle are compared with previous reported experimental data of single also of isolated model using calculation. The nitrogen is second almost homology analysis highest frequent molecular orbital flow play a vital role in determining the various molecular characteristics, including their stability, reactivity, and charge. Homology donating the molecule and sit with this potential. Reflects the electron molecular energy of writing molecule was calculated using the VCL GDP method based on
It's already 10 minutes. Now extra marks will be cut.
These are global reactive descriptor I am calculated and the molecular electrical potential, molecular potential used for understanding charge distribution, predicting reactive side of the molecules, and that's what on orbital analysis also be done. And we are also important tool to investigate the intermolecular charge transfer and delocalization of the electron in the molecule. Some important interaction are in this table. Non-covalent interaction I am also done. Non-covalent interaction which include hydrogen bond interaction, van der Waals interaction, and electrostatic occur between atom and molecule. In this figure, the 2D RDG scatter plot left and 3D colored Iverson plot right, stating non-covalent interaction CMNDP.
So money is okay now. Thank you. Because
Thank you.
you
to stand here before all of you this evening. On behalf of organizing committee, we are delighted to offer a gracious welcome to all of you in the valedictory session of International Conference on Frontiers Research in Material Science and Technology 2025. It gives me the gigantic privilege to invite the session Dr. Shukla, of Science, Hare Krishna, convener, guest of honor, or special guest, Dr. Jevaria, FRMST, Professor Anil Kumar Malik, Organizing Secretary, FRMST, Dr. Neeraj Pawar, grace the dais. Thank you, everyone. The function of prayer is not to influence God, but rather to change the nature of the one who prays. On this note, I would like to call upon dignitaries on the dais to invoke the lamp of wisdom before Ma Saraswati. Thank you very much, everyone, for doing this favor. At the outset, I humbly request Professor Anil Kumar Malik and Dr. Neeraj Pawar to extend a warm welcome to our chief guest, Professor Vipin Chandra Shukla, with a Shrifal, plant sapling, and a token of our gratitude shawl and conference memento. Moving further, I again invite Professor Anil Kumar Malik and Dr. Neeraj Pawar to welcome Professor Hare Krishna, officiating Dean Faculty of Science, with Shrifal, plant sapling, a token of our appreciation shawl, and the conference memento. Now I would like to invite Professor Lokendra Kumar, Dr. Updesh Verma on the dais to please welcome Dr. Mukesh Jewaria, Dr. Mukesh Jewaria, our special guest. So please welcome him with a plant sapling, a Shreefal, and token of our appreciation shawl and the conference memento. Thank you very much, sir, for doing the honors for us. The fragrance of flowers is spread only in the direction of the wind, but the goodness of a person spreads in all directions. With these words, ladies and gentlemen, we are delighted to have Dr. Vipin Chandra Shukla, Scientist G, Department of Scientific and Industrial Research, Ministry of Science and Technology, Government of India, as the Honorable Chief Guest of the valedictory session. I like to call upon Professor Anil Kumar Malik on the dais to introduce our Honorable Chief Guest to all of us.
Thank you, Dr. Kavita. A very good afternoon to all of you present in the hall. Present here on the dais, Professor Hare Krishna, Dean Science, Chaudhary Charan Singh University, Meerut, Dr. Vipin Kumar Suklaji, our today's chief guest, is Scientist G and advisor of DSIR, Ministry of Science and Technology, Dr. Mukesh Jewaria, Principal Scientist, NPL, CSR, New Delhi, and organizing secretary of this conference, Dr. Neeraj Pawar. Of the dais, I can see so many dignitaries, Dr. Sajjan from MDU, Professor Rajesh Puniaji from MDU, Professor Satish Khasaji from D Crust, Haryana, Professor Lokenderji from Central University, Allahabad, Dr. Updesh Verma, and Dr. Anil Yadav, and many more faculty, whom I cannot call upon here. I may forget some names. I'm sorry for that. But all the faculty members, media persons, photographer, here participants. As I have been assigned the duty to introduce our chief guest, it's really my honor and great privilege to introduce Dr. Vipin Chand Suklaji. He is currently serving as Scientist G and head of the various funding schemes and United Nations APCCCTT, Master Science, the Department of Science and Industrial Research, Ministry of Science and Technology, Government of India. By training, he is a mechanical engineer. He completed his postdoctoral research in advanced manufacturing at IIT Delhi. He is actively involved with several prestigious government and academic committees. As an expert, Dr. Sukla is a Senate member of IIT Delhi, serves on the Board of Studies for the Department of Design at NSUT New Delhi, and is part of the expert committee for startup policy at Jamia Millia Islamia University, New Delhi. Additionally, He has also experience to work with the World Bank on national innovation projects. He was invited by Federal Ministry of Education and Research as guest scientist in Federal Republic of Germany to explore possibilities on joint railway technology development project with India. With nearly 28 years of diverse experience, Dr. Sukla has worked across multiple domains and dimensions, including scientific and technology management and innovation promotion and funding, industrial research, testing, and academia. He has very big list of achievements, and because of a limitation, constraint of time, I cannot mention many of them. He's a very dynamic person. He's very gentle person. You can just see from his face. So I really honored to have Dr. Vipin Chand Sukla here to grace this function as chief guest. Thank you very much, sir. Thank you.
Now, I would like to invite Dr. Neeraj Pawar on the dais for presenting the conference report.
Chief guest, Dr. Vipin Chand Suklaji, Scientist G and Advisor, DSIR, Ministry of Science and Technology, Government of India. Professor Hari Krishna Ji, Dean of Science, Chaudhary Charan Singh University, Meerut. Dr. Mukesh Javaria Ji, our special guest from CSR National Physical Laboratory, New Delhi. Professor Anil Kumar Malik Ji, Head of the Department and Convener of this conference. Of the dais, many dignitaries sitting, students, and others. A very good evening to each and everyone present here. This is a very important moment in any event. I am summarizing here what has been done here during 2 days. So this is a very important activity, and I present it before you. In this conference, the conference started with the inaugural session. The inaugural session of this conference, abbreviated as FRMST 2025, it was held in this seminar hall, and it was presided over by Professor Sangeeta Shukla, Honorable Vice Chancellor, Chaudhary Charan Singh University, Meerut. The event began with the worship of Ma Saraswati and Deep Prajwalan by the chief guest, Professor Ashok Kumar Nagavatji, Honorable Vice Chancellor, Delhi Skill and Entrepreneur University, along with Professor Mridul Kumar Gupta ji, Pro Vice Chancellor of this university, Professor Birpal Singh ji, Director Research and Development, Professor Anil Kumar Malik ji, and many other dignitaries and participants present at that time. During the inaugural session, the conference booklet was formally released by the dignitaries. Professor Anil Kumar Malik, convener of the conference, extended a warm welcome to all the participants, including keynote speakers, invited speakers, and contributory speakers. Delivering his address, our chief guest of the inaugural function, Professor Ashok Kumar Nagavatji, Honorable Vice Chancellor, Delhi Skill and Entrepreneurship University, highlighted significant advancements in material science, quoting Nobel laureate Richard Feynman, and the quote is, "There is a plenty of room at the bottom," and Madame Curie, who is another Nobel laureate, "One never notices what has been done, one can only see what remains to be done." In her presidential address, Professor Sangeeta Shukla Madam, Honorable Vice Chancellor, Chaudhary Charan Singh University, Meerut, emphasized the critical need for innovation in material science to ensure sustainable development. The vote of thanks, of course, it was proposed by me, nothing to say about it. The inaugural session was hosted by Dr. Kavita Sharma, who is a faculty in our Department of Physics, Professor Anuj Kumar Sharma, our colleague, Professor Sanjeev Kumar Sharma, who are the co-conveners of this conference, Dr. Yogendra Kumar Gautam, Joint Secretary of this conference, Dr. Anil Kumar Yadav, Joint Secretary, Dr. Vivek Kumar Notial, Joint Secretary of this conference, and many other professors and dignitaries from Chaudhary Charan Singh University, Meerut, and other colleges were also present during the inaugural session of FRMST 2025. This conference comprised of 10 technical sessions and one cultural program with 41 keynote speakers invited from prestigious institutions abroad and across the country, including USA, Europe. These people were present offline, and offline speakers were from Bhabha Atomic Research Center, Mumbai, IIT Delhi, IIT Roorkee, IIT Guwahati, IIT Bhubaneswar, IIT Hyderabad, CSIR Labs, SSPL DRDO, central universities, many prestigious state and private universities. The conference hosted around 180 participants, including keynote and invited speakers from renowned institutes, along with contributing oral and poster presentations, creating a vibrant platform for scientific exchange and collaborations. The technical sessions, the topics were covered as follows: materials for CO2 conversion and H2 production, photonics and biomaterials, terahertz, metamaterials, sensors and detectors, devices, magnetic and multiferroic materials, energy harvesting and storage materials, sensors and detectors, devices, computational materials, 2D materials, topological materials, energy materials, optoelectronics, optical UV detection, and conducting oxide. So from these topics, you can think of that this conference had covered the latest topics in the field of material science and technology. There were three parallel technical sessions across three different halls, featuring a range of keynote talks, invited talks, oral presentations, and poster presentation was today that just finished. These sessions were conducted in both offline and online modes, ensuring broad participation and engagement. On the first day in Hall 1, the first technical session of this conference focused on materials for CO2 conversion and hydrogen production. It was chaired by Professor Prashant Kumar Chauhanji from JIIT Noida. Keynote speaker Professor Tokir Ahmadji from Jamia Millia Islamia New Delhi highlighted carbon-based heterostructures for enhanced hydrogen production via water splitting. Invited speaker Dr. Sunil Kushwaha from CSR National Physical Laboratory, New Delhi, discussed the growth and characterization of 2D materials for sustainable energy applications. Invited speaker Dr. Bharti Singh from Delhi Technological University presented polymer 2D material hybrid systems for self-powered Internet of Things devices. Invited speaker Professor Sushil Kumar from Chaudhary Devilal University, Sirsa, Haryana, elaborated on the reduced graphene oxide supported metal oxide nanocomposites with enhanced photocatalytic activity for environment remediation. The second technical session on magnetic and multiferroic materials was chaired by Dr. Mukesh Javaria, who is our special guest sitting on the dais. Keynote speaker Dr. Amit Kumar from Bhabha Atomic Research Center, Mumbai, highlighted neutron diffraction's role in studying magnetic materials and spintronic devices. Keynote speaker Professor Rajendra Dhaka from IIT Delhi discussed lanthanum doped cobalt double perovskites showing tunable magnetic and electronic properties. Invited speaker Professor Vivek Kumar Malik from IIT Roorkee presented complex spin reorientations in orthoferrites and orthochromites, highlighting their potential for spintronics. Invited speaker Dr. Yugandhar Bitla from Central University of Rajasthan explained how vanadium doping in lanthanum strontium cobaltate oxides enhances cluster glass behavior and magnetocolor performance. An online key talk on tetrapods based smart materials was delivered by keynote speaker Professor Yogendra Kumar Mishra from University of Southern Denmark. In Hall 2, technical session on photonics and biomaterials, terahertz, metamaterials. This session was chaired by Professor Anurag Pawar from JIIT Noida. Keynote speaker Professor Ranjan Jha from IIT Bhubaneswar discussed enhancing single photon emission using gold nanorod dimers, improving photon count rates, and polarization for efficient quantum networks at room temperature. Invited speaker Dr. Mukesh Devaria presented the development of a terahertz frequency comb generating stable terahertz pulse trains from zero point 0.1 to 3.0 terahertz using photoconductive antennas, crucial for high precision frequency metrology. Invited speaker Professor Gagan Kumar from IIT Guwahati explained quasi bound states in the continuum modes in terahertz materials using symmetry breaking techniques to achieve high Q resonances for advanced photonic devices. In the second technical session on energy harvesting and storage materials, chaired by Dr. Pradeep Kumar, Principal Scientist, CSIR Embry Bhopal, speakers highlighted cutting-edge advancements in multifunctional materials, energy devices, and sustainable sensing. Keynote speaker, Professor Akhilesh Kumar Singh from IIT BHU, discussed complex oxide ceramics for sensors, energy storage, and photovoltaic applications. Invited speaker, Dr. Rajinder Pawar from Central University of Rajasthan presented work on nanostructured photoelectrodes for efficient solar water splitting. Invited speaker, Dr. Waris Pawar from Graphic Era University, Dehradun, introduced flexible ionic polymer sensors for wearable energy harvesting, sensing, and water purification. Invited speaker Professor Anurag Gord from NSUT Delhi covered supercapacitors, hybrid energy storage devices, and hydroelectric cells. Keynote speaker from USA, Florida State University, USA, Dr. Ajit Kaushik showcased AI-enabled smart sensing for health and environmental monitoring. In Hall 3, the session on sensors and detectors devices was chaired by Professor Vivek Kumar Malik from IIT Roorkee. Keynote speaker Professor Satish Kumar Dubey from IIT Delhi presented Raman-based sensing modalities using SERC probes for rapid detection of explosives and single crystal scintillators for nuclear radiation detection. Invited speaker Professor Vinod Singh from Delhi Technological University highlighted palladium carbon core shell nanoparticles for enhanced hydrogen gas sensing. Invited speaker Professor Lokendra Kumar from University of Allahabad covered hybrid perovskite materials for solar cells. Invited speaker Professor Navendu Goswami from JIIT Noida introduced copper oxide nanoparticles synthesized via electro explosion, showcasing their multifunctional properties for advanced device applications. The second technical session, Sensors and Detectors, Devices and Others, was chaired by Dr. Sunil Singh Kushwaha from CSR National Physical Laboratory, New Delhi. Keynote speaker, Professor Kedar Singh from Jawaharlal Nehru University, New Delhi, delivered the keynote talk on carbon-based heterostructures for hydrogen production. Invited talks included Dr. Preetham Singh from CSR National Physical Laboratory, New Delhi, on magnetron sputtered metal oxide thin films for carbon monoxide sensing. Professor Pawan Kumar Fulria from Jawaharlal Nehru University, Delhi, on irradiation-induced chemical disordering in nuclear ceramics. And Professor Sandeep Chokar from JIIT Noida discussed 2D materials like vaccines and transition metal disulfides for catalysis, sensing, and energy applications. The session highlighted innovative materials and techniques for sensors, energy devices, and environmental monitoring. Keynote speaker Dr. Anton Gradsic from Slovenia discussed his ideas about the artificial nose. The evening of the first day of FRMST 2025 was filled with soulful music, yogasana, and yoga dance performances hosted gracefully by our student, Ms. Vanshika Bhardwaj and Ms. Akriti Banjaria. Dr. Abhinav Sharma and his group from Noida delivered a mesmerizing musical performance. Rishi Yogshala Meerut presented stunning yogasana and yoga dance acts performed by talented artists. The cultural programs culminated with felicitations of the artists. On day two, technical session on computational materials, 2D materials was held in this hall and it was chaired by Dr. Mohit Tyagi, senior scientist at Bhabha Atomic Research Center, Mumbai. Keynote speaker, Professor Abhi Desarkar from Institute of Nanoscience and Technology, Mohali, delivered the keynote talk on DFT insights into piezoelectricity, spin orbitronics, and valley physics in 2D materials. Invited speakers, invited talks included Dr. Abhishek Kumar Misra from UPS Dehradun on computational studies on transition metal oxides and 2D materials for carbon capture. Dr. Pradeep Kumar from CSIR MP Bhopal discussed graphene and MXene for hydrogen storage and electromagnetic shielding. Dr. Rajgopala Reddy Silam from Central University of Rajasthan discussed triplet state generation in BODIPY dimers for enhancing solar energy applications. The session highlighted cutting-edge advancements in computational material science. The topological materials and energy materials session chaired by Dr. Yugandhar Bitla from Central University of Rajasthan highlighted innovative research in advanced material, and it was held in the Department of Physics Seminar Hall. Dr. Pradeep Das from Guru Ghasidas University, Bilaspur, presented topological nodal lines feature in nickel selenium semimetal, revealing multiple scattering mechanisms, weak anti-localization, and unique nodal line structures confined by DFT. Invited speaker, Dr. Braj Bhushan Singh from HBTU Kanpur demonstrated spin to charge conversion via the inverse spin Hall effect in polycrystalline Bi2Se3. Invited speaker, Dr. Rajesh Kumar from Punjab University showcased tungsten and molybdenum oxide nanostructures for efficient dye removal. Invited speaker, Professor Satish Kumar Khasaji from DCRUS Murthal discussed oxygen deficient NBT MFO nanocomposites, showcasing enhanced water splitting capabilities in hydroelectric cells, paving the way for sustainable energy solutions. In another hall with technical session on optoelectronic materials, UV detection, conducting oxides was chaired by Dr. Rajendra Pawar from Central University of Rajasthan. Keynote speaker, Professor Sai Santosh Ravi from IIT Hyderabad, delivered the keynote talk on silver bismuth code lead halide perovskite nanocrystals for cell-powered photodetectors, showcasing enhanced responsivity and detectivity. Invited speaker, Professor Rajesh Punia from Maharishi Dayanand University, Rohtak, discussed electronic and ionic transport in oxide glasses for energy storage. Invited speaker, Professor Sajjan Daya from MDU Rohtak, presented study on zinc cobalt oxide drawn on N-type silicon substrate for UV photo detection application, highlighting solution-based fabrication and cell-powered UV detection devices. The session showcased cutting-edge materials for optoelectronic and sensing applications. In the poster presentation that finished just now, the posters were judged by, there were around 90 posters, and all the posters covered the various themes of the conference. The posters were judged by distinguished panelists, and these panelists are Professor Satish Khasa from DCRUS Haryana, Professor Rajesh Punia from MDU Rohtak, Dr. Yugandhar Bitla from Central University of Rajasthan, Dr. Pradeep Kumar from CSR MP Bhopal, Dr. Hemant Singh from Sri Dev Suman Uttarakhand University. So there were 5 panelists and they have judged each and every poster very critically, very crucially. And so out of all the poster presentations and the oral presentations which were presented here, 6 poster presentations were selected. There is no 1, 2, 3. All 6 are the best posters, and 3 presentations from the oral presentation category were selected by the respective session chairs. So three presentations from the oral presentation category and 6 posters from the poster presentation category have been judged by the respective judges, and they will be shortly awarded by the chief guest. So this is all about in brief the summary of the conference report that I have presented, that this work has been done during the 2 days. So with this, I conclude my talk. Thank you. Thank you very much.
Thank you, Dr. Neeraj, for the for proposing the conference report. Now, may I call upon some of the participants on the dais to share your experiences, views about the conference participation. We would be very happy if some of you please come up on the stage and share your views about the conference.
So, good evening, everyone. My name is Anjali. I am from University of Petroleum and Energy Studies, Dehradun, Uttarakhand. So, attending this international conference on frontier research in material science and technology was an enriching experience. I've learned so much and had great conversation that will definitely shape my future. A big thanks to the organizing team for putting everything together. And I'm excited to take what I have learned and apply it to my work. Looking forward to more opportunities like this. Thank you.
Anybody else, please come on the dais from the invited speakers.
Good evening to all. I am Mukesh Verma from Central University of Rajasthan. So this was very nice and well organized conference. Speakers were excellent. It was valuable and enjoyable experience, and I experienced very good here. And I appreciate to learn from this conference and from all of you. So thank you. I thank you, the organizers, and all of you.
So, very good evening to all of you. First of all, I would like to thanks organizer, Department of Physics of CCS University for organizing such a wonderful international conference. And I think they have invited speakers throughout the India from various prestigious institutes. So I personally had very good interaction with all the speakers, and I think all of you also had good interaction with all the speakers. And students maybe they learned from like all the speakers many things, many very good keynote lectures, invited lectures, and in apart from that, like accommodation, food, it was very good. And poster session, actually, many of the students presented very good posters and they are doing very good work. So overall, actually, it is a wonderful conference. And the main, not last, actually, I'm coming Meerut since 2005. So this is the first time actually I am here in Department of Physics. So personally, I feel very good and proud to be here. Thank you very much.
Now, I humbly request Professor Rajesh Punia, who is among the panel of judges, to please come up on the dais and share your experience, your views about the poster presentations.
Thank you. All the scientists and professors on the dais and off the dais and the dear participants. The poster session was very good, and overall the conference was well organized and very good food, very good stay. And one more thing I want to add that before coming to this university, Meerut University, we think that Meerut University is not in good shape and the perception is not good. But after coming here, we have very good memories, and your university is doing wonders. And I especially want to congratulate Professor Anil and his team for organizing this event and making fames of this institute throughout the India and abroad. So this gives you a very good opportunity, this type of conferences. So it helps you in changing the perception of the institute. So now we have very good memories of CCS University Meerut, and we all will be your brand ambassadors. So thank you all.
Thank you so much, sir, for your kind words. We are happy that we could change your perception. Talent and skills are the crops that are nurtured, groomed, and given all possible opportunities to grow and bloom. This is a much awaited moment as it gives a sense of achievement and a sense of responsibility towards fulfilling further commitments. We acknowledge and encourage the talent of young scholars for their academic and research excellence in the form of Best Oral and Poster Presentation Awards. So, as Dr. Neeraj already told in his report, in the conference report, that organizers of FRMST 2025, with the kind consent of Honorable Vice Chancellor Professor Sangeeta Shukla, announced 3 Best Oral Presentation Award and 6 Best Poster Presentation Awards. So, may I announce the name of the best oral presentation winners? Can we have the certificates? For doing the honors, I would like to invite chief guest of our valedictory session, Professor Vipin Chandra Shukla, Professor Hare Krishna, Dr. Mukesh Jevaria, Professor Anil Kumar Malik, Dr. Dheeraj Pawar, Professor Rajesh Punia, please you come up on the dais for doing the honors. Dr. Yugandhar Bitla, you please join the dignitaries on the dais to honor the young researchers. So first, I'm going to announce the winners of Best Oral Presentation Awards. So the winners are Mr. Kuldeep Kumar from CSIR NPL New Delhi, Ms. Sarita Sindhu from CCSHAU Hisar, Ms. Sarita Sindhu, you please come up on the dais. Is she here? Mr. Kamal Kumar from UPES Dehradun, Kuldeep, you can please wait for a while because we can have a group photograph with the dignitaries. Now I am happy to announce the names of Best Poster Presentation Awards, and the winners are Miss Richa Bharti, P5. Miss Indu Kumari, poster 39. Vikas, P41. Abhishek Sharma, P56. Oh, sorry, Abhishek Dhasmana. Krishna Kumar Yadav, P79. Pavan Kumar, P46. I think we should encourage the winners with the huge round of applause. Thank you. Now, I would like to invite Honorable Chief Guest, Dr. Vipin Chandra Shukla, on the stage to address the gathering.
Very good evening to all of you, all the distinguished experts on the dais, of the dais, dear students, ladies and gentlemen. It is indeed a pleasure for me and also an honor that I'm here. And it is always very interesting to interact, especially with students. I know that a lot of energy which is lying in our country that is under youth. So that's why we feel that we also get some opportunity to not only to encourage students, youth, but also to learn a lot from them. And still, there is a scope for both the parties to enrich each other with their experiences, with their knowledge. So today, I will talk in that way that we both are on the same platform. The only thing is, I am sharing my experience to you, and probably sometime you can share your experience to your gurus, your teachers, your mentors. I'm, I'll take 2 minutes to talk about my department and why I thought I should talk about my department because I am from Department of Scientific and Industrial Research, that's DSIR. This is under Ministry of Science and Technology, Government of India. And the department has lot of activities, but primarily uh, it has 37 CSIR labs also. So CSIR basically is of your interest because I see that most of you have potential to become a good scientist. And what I saw during the comprehensive conference report from Dr. Neeraj, that I will appreciate the organizing team that they have beautifully uh,
program this event. We have lot of CSIR labs, scientists involved here, IIT professors involved here, professors from other academic institutions are involved, even government officials are involved. That is something which you look for your career enhancement also. So my department is basically, I would suggest you that there are under physical science, because you all are mostly from physics background, you should look for some of the labs of CSIR. Uh, those are doing work under physical sciences. So NPL is one example. CSIO is there. Probably CE may be very helpful. AMPRI is another organization. So the purpose of event is also that not only to win some certificate or award, but also to intermix, to mingle with the experts who are coming here despite of their busy schedule. So that is another opportunity for you. For faculty, our respective faculty, I'll just say one sentence that we are also running some funding support schemes also. So you can take advantage of that. Ultimately, we believe that if we are supporting you, in a way, we are supporting to the youth of India, because they will work under you under those projects. Now, while I was listening all the reports, I saw two photographs here. One is our former Prime Minister, Honorable Atalji, and another former President, Dr. APJ Abdul Kalam, sir. And why I thought I should talk something about these two great personalities, because I am lucky that I got chance to interact with both of them. When I was 12, in class 12, I got a chance to meet to Atalji. He came to my school in Kanpur, and at that time we demonstrated some of the lab experiments because we were in 12th class, so it was in science background. So we were asked to do some experiments, some test tube. We still I remember with some test tube, and he asked a lot of question, motivational things. And at that time, since we were 16, 17 years old, we asked that, can we write to you in future? He said, yes, you can write to me. Then we asked, okay, we will write to you, but will you answer? He said, yes, I will answer. And then we forgot. We thought that probably he might have said all these things just for the sake that we should be feeling good. But believe me, after 3, 4 years, when I was in third year of my engineering, I started writing to Atalji. And each and every letter of mine was replied back. Each and every. And let me tell you, my last letter was to him. I still remember during December 1995, when I wrote that my heart says, हिंदी में लिखा था कि मेरा दिल कहता है कि इस बार आप प्रधानमंत्री बनेंगे. उस समय इनका बर्थडे भी आता है. एक्चुअली बर्थडे विश किया था एट द टाइम, एंड ही रिप्लाइड बैक दैट आल्सो. ही सेड कि विपिन जी, आपकी शुभकामनाओं के लिए बहुत बहुत धन्यवाद, क्योंकि मैंने उसमें जन्मदिन के साथ उनको भारत का प्रधानमंत्री होने की भी शुभकामना दी थी. एंड दैट इज बाय कोइंसिडेंट वॉट एवर से 13 डेज के लिए उसके बाद 96 में वो बने थे. व्हाट आई वांट टू कन्वे कि जो ग्रेट पर्सनालिटीज होती हैं, most of the time we feel that they are big people, they will not listen to me. But no, this is wrong perception. You write to them, you do some follow up with them. They are big people, they may be busy, definitely they are busy. And now in this digital era, definitely they are much busy, but we'll have to write to them. So that is one example. But interaction with Dr. Kalam is something fantastic experience for me. When I joined my government service, I got a chance to interact with him. He was chairman of governing council of TIFAC that time. And when I met him, he spent around 40 to 50 minutes with me. And I came at the time from private sector. So I was not much well versed with the government system. So probably if I had known government system, I would have not talked that much in front of him. But I was from government. Then he taught me, and can you believe, again, when he came to know that I am from Kanpur, few of my friends who are from Kanpur may understand. He asked me about Ganda Nala place. There is one place, Ganda Nala. So I was surprised because I born and brought up in Kanpur, but I never went there. But visionary people, they lived there even for some small duration. They know the pulse of the city. They know the problem of the city. They know the problem of the system. Then we had many other meetings also. In one of the meetings, he told me one thing which I followed still, which still I follow. He said, Vipin, if you cannot the best in your career, because everybody cannot be the best in one field, then you try to become the best system integrator. What he meant by that, that sometimes it happens. Why I'm saying some of you got certificate and many of you did not get. That is not end of your journey. See, at this point of time, someone has won. It means he or she might have done something better than you, but it does not mean that you cannot do. And after some time, when you are a little bit more grown up, so sometimes it happens that we say that, yes, now I'm in this field, I cannot change my field. Okay, if you cannot change your field, you cannot be best in that field, then you become the best system integrator. You should know. Now, like our Dr. Mukesh, he is doing great mission projects. And under those projects, number of different sub activities are involved. He necessarily he may not be best in each and every sub activity, but he is the best in system integrating the system. That is what Dr. Kalam told me, that never lose your heart. Whatever is available with you, you try to integrate that thing, and one day you will be something great. You know, of the very famous book written by him is Vision 2020. And why he wrote? Because when he was interacting with school kids of class 7, 8, 9, one girl asked him that, how do you see India in coming 20 years' time? And that ignited his mind that I should think about this. Then he wrote, then he did a lot of brainstorming. He wrote that book. And I will say we should have proud on his vision that he wrote that thing somewhere in mid of 90s that by 2020 India will be a developed country. Probably there is good chance that India will be a developed country. And now we can see, at least we can say that yes, we are on the verge of becoming a developed country. At least we are not underdeveloped country. So that is the vision of great people. And I would say that whenever you get time, you try to read books written by such type of visionary people that will give you lot scope for your future. And another example I will just cite to you. In present arena, you all might have got all these achievement of ISRO, and Dr. S. Somnath was head of ISRO at that time. you try to interact with people like him also. That will give you much more broader vision about your career, your future. So by saying all these things, what I want to say that you have lot of plenty of scope for future. If your energy level may not be all the time make you on the top, you try to create synergy that will bring you to the top of some platform, and never lose your heart. You keep on doing hard work. So that is what I thought I should convey, because all these technical things, much more knowledgeable people have already discussed with you, presented all the things. I think that that is something motivational thing I should share with you. And one thing I want to say, when I got invitation from Dr. Professor Malik that I should come, so I came here. I was happy actually. I wanted to come to Meerut University because sometimes you feel that this is a university, and there, because mostly in Delhi we interact with Delhi University people and some other universities, but universities like Meerut University and, for example, Kanpur University, all these are having a great mix, a wider mix of students, and where I think more possibilities are lying. So I came here with really in happy mood that yes, I am going to. And last time I came here on official visit, I think probably 2009. So what one thing I have observed that I want to share with you. In 2009, I came and hall was occupied with young people like you at that time also. It was Hindi reverse somewhere I came. And I want to share that everybody was very keen, listening each and every word. It was in 2009, and after 15 years, I'm again coming here. I'm seeing the same behavior from you. You all are very sincere. That is that is from my experience also. I keep on visiting many places. I can say one thing. After 15 years, I can say that yes, you are still on the same track. You have that potential. Sincerity will take you to the newer heights, which probably others may not get. So please maintain this thing. Try to listen people and try to pose your queries also, so that proper flow of information discussion should be both ways. With all these words, I wish you all a very great success in your life, in your career. Thank you.
Thank you very much, sir, for your suggestive, encouraging, and appreciating words. Gratitude is the fairest blossom which springs from the soul. With these words, as we come to the close of our valedictory ceremony, I invite Dr. Anil Kumar Yadav on the dais to propose the formal vote of thanks.
Thank you, madam. So now we have to reach at the last of our conference. Good evening, everyone. As we conclude this remarkable two-day conference on frontier research in material science and technology, it is my privilege to extend A heartful vote of thanks on the behalf of Department of Physics, Chaudhary University Meerut. This conference was organized with the aim of bringing together leading scientists, researchers, academicians, and industry experts to explore the latest advancement and emerging trends in material science and technology. For the past 2 days, we have witnessed the insightful discussion, groundbreaking research, presentation, and fruitful collaboration that will undoubtedly contribute to the advancement of this ever evolving field. First and foremost, I extend my deepest gratitude to our Honorable Vice Chancellor, Professor Sangeeta Shukla, for your unwavering support, leadership, and inspiring words. Your encouragement has played a crucial role in this making this event a success. A heartfelt appreciation to our chief guest of day one, Professor Ashok Kumar Nagawat, Honorable Vice Chancellor, Delhi Skills and Entrepreneurship University, New Delhi, and day two, chief guest Dr. Bipin Chand Shukla, Scientist G, Department of Scientific and Industrial Research, New Delhi, for honoring our with your presence and sharing your valuable insight, which have greatly enriched our understanding of this field. We express our sincere grateful to our keynote speakers, distinguished guests, and panelists who joined us online and offline from out of India, like USA, Europe, and from country VRC, Central University, DRDU, and renowned state universities for their expertise and thoughtful working contribution. Your discussion have provided us with a new perspective and have inspired future research. A big thank you to our senior session chairs, paper presenters, and participants for your valuable inputs and active engagement throughout the conference. Your research and discussion have made this event intellectually, intellectually stimulating and insightful. We extend our heartfelt thanks to our sponsors such as CSIR New Delhi, PM Usha, IR Tech New Delhi, and partners and collaborators whose generous support has been instrumental in organizing this conference successfully. A special appreciation to the media representatives for covering and promoting this conference, ensuring that the knowledge shared here reaches a wider audience. We also acknowledge the hard work and dedication of our organizing committee, technical team, and volunteer, and especially our PhD and MSc students who are sitting here. We have worked who have worked tirelessly behind the scene of ensure the seamless execution of this event. Your efforts are truly commendable. A warm thank you to the non-technical staff, including the administrative team, hospitality staff, and logistic coordinators who have provided crucial support and made this conference comfortable and well-organized experience for all. Finally, to all attendees, researchers, and students, your enthusiasm, active participation, and thoughtful-provoking discussion have been the driving force behind the success of this conference. As we conclude, let us take forward the knowledge shared, the collaboration formed, and inspiring gained to the further push the boundaries of the material science and technology. This conference may be ending, but discussion, research, and innovation it has sparked will continue. Once again, a heartfelt thank you to each and every one of you, and especially to our vice chancellor and chief guests and uh, speakers, participants, your unwavering support and commitment to academic excellence. Wishing you all success in your future endeavors, and we hope to meet again in future edition of this conference. Goodbye and safe travels. Thank you all.
Thank you, Dr. Yadav. The end of a story is the new beginning for many others.
Although a formal thanks ceremony is over, I'm sorry and I really take excuse from the dais. And we are also very, very much thankful to our Honorable Vice Chancellor who has given us free hand to spend whatever expenditure comes to on this day of the conference. He basically outrightly never take any friction of second to give the permission, whatever permission we need during this conference. So we are really thankful to this to the great lady, Dr. Sangeeta Shukla, and because of her free hand, we could materialize these things in a very short span of time. So we are very much thankful. We are also organizing committee is also thankful to our Dean Science who spare time to come here because in a very short notice I called him today. So you are supposed to be guest. So I'm really thankful for your time sparing time on a very short notice. Obviously, most of the thank ceremony is over. Thank you guys who make or who just have the patience every time participants, our students. Some mistakes may be there, and I believe that in future we will also try to improve whatever we can for next such events. Thank you very much.
I once again repeat, the end of a story is the new beginning of for many others. At this note, we happily announce the upcoming organization of upcoming conference in September 2025. We would be very happy if the participants once again give us this opportunity to join our conference. So everybody, yes. And we humbly acknowledge the receipt of grant from DSIR for organizing this conference. We are very much thankful for providing this funding to us. So on the behalf of organizing committee, we sincerely thank the dignitaries on the dais for being with us this evening and enlightening us with their enthusiastic remarks. Before signing off, I would like to request everyone, please stand at your places in the respect of national anthem. Thank you very much. मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे Thank you. You all are invited to join us for a cup of tea. I think high tea we have.